All right. Good morning, good afternoon, good evening, everyone. It is awesome to be here with you today at the EDA Summit 2023. Today, you are here to learn about the importance of thinking about patterns when building serverless event-driven applications. And by the end of this conversation, you'll know why they are so important, what it means to use a pattern, and how you can think about your systems using patterns. I'm James Eastham. I'm a senior cloud architect at Amazon Web Services. Let's get straight into it. And I actually wanted to start today with a short story, and that's about how I learned the importance of integration patterns when building serverless and event-driven applications. So a young, naive James was working on a system for a customer before I worked for AWS. And this customer had a pretty simple requirement. They had one service that needed to send an email based on a record in a database table. And after the email was sent, it needed to mark that record in the database as sent. And because I was thinking about things all serverless, all event-driven, all asynchronous, I decided to implement that with two separate services with some asynchronous message passing between the two. So once the email had been sent, the email service published an event, and the original service then marked the record in the database as sent. Sounds simple, right? Well, as it turns out, a slight misconfiguration in the response event processing meant that no emails actually ever got marked as sent. Emails kept getting sent over and over again until I actually realized I had 100 emails sat in my inbox waiting for somebody to look at. And thankfully, this only affected a small number of my customers, but it taught me a valuable lesson, and that was that the actual application code, the compute, was working absolutely fine. The problem came from the integrations and not me thinking carefully enough about how these integrations were going to work. An old mentor of mine once said to me, it's not the boxes on an architecture diagram that cause issues, it's always the lines. So with that in mind, we're going to start at why it's so important to think about these lines and think about these patterns in your serverless event-driven systems. And to do that, we're going to go all the way back to how we used to build systems before cloud-native, event-driven serverless compute, where everything ran in a single process. Life was so much simpler then. Integrations may have been as simple as a method call from one part of your application to another. Everything was within that single process. If the method call failed, we could handle that easily, crash the application. Everybody knew about it. The only integrations we might have had to worry about, maybe to a web layer or a database layer. But the points of failure, at least in this simple example, are just two external integrations, one to the web, one to the database. As we started to move towards more service-oriented architectures and microservices started to take over the world, that single process is now split down into separate business context-focused services. What was once a simple method call is now a remote procedure call over a network, possibly over HTTP. And as any of us who know who've worked with a network for any period of time, networks are unreliable. Networks add latency to your system. So now we've got these independent pieces of functionality split out over a network. We've both introduced more lines, more integrations, and put that over a less reliable integration method. And as we take that one step further to serverless and event-driven applications, this increases exponentially. As well as having the lines between each service and each business context, we now have these additional lines within our services and context. The application code might have got much simpler, but there's now more integrations that are more complex. We think that event-driven systems are the best way to build applications in the modern cloud-native world. And we also start thinking about our systems more asynchronously. And because of that, we introduce more complexity into these lines, and we'll have a look at a couple of them complexities that we add. The first is with consistency and latency. So when we're doing things in a single process, we know that as soon as a method completes, let's say we're writing a record to a database, we know that that's happened because the write completed successfully, or we got a 200 response back from an API. That's a strongly consistent transaction. We're guaranteed that that's happened. But with asynchronous event-driven systems, we need to start embracing eventual consistency. Now, to talk about strongly consistent and eventually consistent, I've got a little analogy for you. Let's imagine for a second you're walking into a store or a supermarket and you need to buy some things. So you collect up all the things you want to buy and you go to the cashier. Now, at this point, I might open my wallet and I might take out some money, some cash. If I hand over that money to the cashier, I know at that moment in time that that money has absolutely, definitely left my hands. I no longer have that money and the store now has that money. That's a strongly consistent transaction. Whereas if we take that same situation and I was to pay with a credit card or a debit card, that would then be eventually consistent, because all that is a guarantee that at some point in the future, that money is going to leave my account and hit the account of the store. And that's what we need to embrace when we start thinking asynchronously. If we're communicating from one service to another through some kind of event bus or message bus, we need to embrace the fact that there is no way we can guarantee that any other parts of our system have received any events from our system. And we also introduce latency as well, as opposed to what was once a simple in-process message call. That is now running over a network plus a message bus plus maybe another network at the other side. And if any of these components then fail, much like my example in the email sending at the start, how do we know about that? How do we determine that there's been an error in these integration points? These are some of the complexities that get added when we start thinking asynchronously and event-driven. And we also may need to integrate with other components of our system that might not be ready for event-driven systems. Maybe we've got some old, horrible monolith that nobody wants to touch and work with, but we need to integrate that with the rest of our systems. What patterns and processes do we have to help enable these communications between maybe legacy systems and something which is potentially infinitely scalable running on serverless? So to summarize our why, with serverless event-driven systems, we've got lots of small pieces of loosely joined application code. And we're thinking about these integrations completely asynchronously. And what that then means is that we have much simpler boxes. Our application code itself is much simpler, but we've increased the complexity of the lines of the integrations. So now we have a why. So let's talk briefly about what we mean by a pattern. And to pull a definition straight from Wikipedia, a pattern is just a regularity in the world, in human-made design or in abstract ideas. As such, the elements of a pattern repeat in a predictable manner. And as humans, our brains are fundamentally built for things like pattern recognition. It's a special ability of our human brain to not only find patterns, but figure out in a logical way what those patterns suggest about what's going to happen next. The neocortex, the outermost layer of our brain, is found only in mammals, and it's responsible for this ability for us as humans to recognize patterns. And patterns are just mental shortcuts that allow our brain to quickly realize what is happening and also, importantly, infer what is going to happen next. And patterns aren't a new thing in software at all. Back in October 1994, the famous Gang of Four book was published on design patterns in object-oriented software. And what this book started to do was to provide a language around building object-oriented software. Many of the patterns in this book are still widely used in programming today. and it enabled developers to communicate with each other in a common language, regardless of the programming language used. So I'm a .NET developer, but if I look at a piece of Java code and I see a builder pattern, I can infer what the intention of that piece of code is. Fast forward to 2003, we had domain-driven design, the famous Big Blue Book. And that gave us a language and a set of patterns around software architecture and the systems themselves. It allowed us to think about the internals of a given system and how we can split down our system into business-focused components. It also introduced the idea of the ubiquitous language, which is something I'll come back to in just a moment. Also published in what turned out to be an immense year for software books was Enterprise Integration Patterns, published in 2003. And this book is a manual on all the different patterns for integrating parts of our applications together. Now, with a combination of these three books, we have the language and the technical details to talk about all the layers of our software stack. Yet somehow we seem to, at an integration level, at an architectural level, lose these details. We tend to dive straight into implementation details and not think about the patterns that we actually want to implement. And these integration patterns are the language that enable us as architects to explain our intent for a system. The underlying services are just implementation details. So that idea of ubiquitous language that I talked about, that idea is that using a common language between developers and business experts helps align the communication and understanding of a system. Using a common language between business and the technical allows people to easily express their intentions, and for developers to implement them intentions using a familiar language. And event-driven architecture pushes that boundary even further. We're now making business events the first-class citizens in our systems. If everything in our system is driven by business events, by a common language, we can start to ask questions like, what happens after an order confirmed event? What happens if an order gets cancelled? And the business people can talk back in a language that they understand. Yet, as I said, somehow when we talk about our architectures and we design architectures, we tend to dive straight into the implementation details. We know about the benefits of ubiquitous language, about how these patterns can help our brains understand what's going to happen next. Yet we default to talk about SQS or Kafka, SNS or EventBridge, and we forget we've got this higher level of communication. And there's two benefits to starting thinking in patterns. I've worked with some excellent engineers in my time building really complex systems that truly solve business problems. Some of these systems were built on premise, some of them running on cloud servers, and some of them fully serverless cloud native systems. Now, what happens when these engineers need to move between different systems or different organizations, or maybe a new developer joins the team who isn't familiar with that cloud provider or that service? Talking about a system through these implementation details really increases the load on people as they start to do these things. Whereas talking about a system through the lens of patterns gives us that common language that all developers can understand and work with. If I was to join the team and the system was described as using a transactional outbox that published a notification message to a point-to-point message channel, you could kind of understand what I was intending to do with them patterns. But if I said, if the system stores a message in DynamoDB and then uses DynamoDB streams to trigger a Lambda function, which then processes the message and publishes it to SQS, you've got absolutely no idea what I'm talking about unless you're familiar with AWS specifically. If people leave the team, architects move on, that intention of a system, the way these components talk to each other, can easily be lost. And thinking about things in patterns also helps us to start to remove bias from our systems. So I work at AWS. And Amazon EventBridge is an AWS service that is really versatile, and it provides publish subscribe functionality, and it can fit the vast majority of use cases. And it's my default for pretty much every inter-service communications required. But this is a bias. When I'm designing an architecture, I have a bias, conscious or otherwise, towards Amazon EventBridge. If I was to design my entire system around EventBridge, what happens if suddenly EventBridge isn't an option? Maybe the security team don't like it, or it starts to cost too much. I now have that sunk cost bias towards an architecture including EventBridge. If, however, I simply thought about my system through the lens of I need publish subscribe, and I documented my intention just to have publish subscribe in my system, that's what I know I need. And the implementation details are then driven by the business requirements, not by the preference to a given service. That's an awful lot of theory. So let's get into some actual practical examples now, and we can look at how we can actually use some of these integration patterns in our architectures. And to do that, we're going to set up a set of different requirements that we need in this theoretical system. So we need to have asynchronous communication between two services. This is an event-driven summit, after all. As part of that, we want durable message processing that ensures each message is only processed once. Of course, we want error handling to make sure that we know when things are going wrong and we know when there's been any problems. And our sending system needs to receive some kind of notification back from our receiver when the work has been completed, when the work's been done. And on top of all of that, at the same time the message gets sent, we also need to persist a record to a database in our sending system. So we need to know that when the record's in the database, we can guarantee that the event has also been published, and vice versa. So if I put my AWS hat on, I can probably jump straight into some kind of architecture diagram that looks something like this. And this would support all of the use cases described, and it will probably work with this simple example. We've got a DynamoDB database, and we're using a stream from our DynamoDB database to start a step functions workflow. Within that workflow, we're publishing a message to Amazon SQS. SQS has a dead letter queue assigned to it. And then we've got our receiver over on the right-hand side that's doing the work and then sending a message back to our workflow to say, yeah, I'm done, I can continue. Now, I'm sure there's some of you listening who may not be familiar with AWS, and looking at this, you can probably infer kind of what's going on and what the services do based on the requirements just described. But if you came at this fresh with no knowledge of AWS, this could prove quite difficult to start to get your head around and understand what the system's actually intended to do. So let's look at this same architecture diagram, but in a slightly different way. Instead, now we've got the exact same architecture diagram, but we're designing it now using well-known and well-understood patterns instead of implementation details. Funnily enough, when I was actually building out this deck, I created the AWS architecture diagram and then created this diagram using patterns, and actually realized I had a missing piece in my architecture, and that's the response channel. We want messages to be passed durably between our systems. We had durability on the way out. We had no durability coming back. So even starting to think in patterns, thinking about our business requirements, actually identified an oversight in the system. So let's quickly walk through what's going on in this architecture diagram now. We know we've got our primary database where our data is going to be stored. And then we're using a transactional outbox pattern to make sure that the message gets published. And we'll talk about some of these patterns in more detail in the coming slides. After the message has gone through our transactional outbox, we will kick off our workflow, and our workflow is going to send a message to a point-to-point request channel. That request channel has a dead letter channel associated with it, And then we've got our receiving application on the right-hand side, which is going to do some work and then durably send a message back to our response channel. The response channel is owned by the sending service, and our workflow then continues. And even within the body of the message itself, we're going to be using some patterns. We're going to be using a correlation identifier. Because this is asynchronous, we need a way to correlate a given instance of our workflow back to the work that's being done in our receiving service. And we're also going to use a return address. We need a way to tell our receiver where to send its response to, in this case, the response channel. So that data is actually going to be packaged into the message body itself. You can see now we're talking about this system with a set of patterns that we could start to understand. We could look at this and kind of work out what's going on. We've got a database, we've got some kind of outbox that's starting a workflow, we've got one message channel on the way out, and then another message for the response. So let's look at some of these patterns in a little bit more detail now. So we'll first look at the transactional outbox pattern. And the transactional outbox is a pattern that allows a closer tie and higher level of guarantee between persisting a record to a database and publishing an event off the back of that. So let's imagine you're writing some code and you need to publish an event and store a record in the database. Well, which line of code comes first? You store the record first and then publish the event, but then what if the event fails to get published? And the same the other way around. So the transactional outbox helps to solve some of these problems. You can do this with a traditional relational database. You can do this with a NoSQL database. If you have a relational database, you might have two separate tables in your database, one being a orders table for your actual record, and then maybe a second table called outbox. And then that way you can write to both tables in a transactionally consistent way. You guarantee that the message is in your outbox as the record is stored. And then you'd have a separate process reading from the outbox table and only marking the record as sent in the outbox once the event has been successfully published. And you could also implement that using change data capture in a relational database if it supports that. And that's what we're doing in this example here. We're using Amazon DynamoDB, which is a NoSQL AWS managed database. And DynamoDB has a feature called DynamoDB streams. So when the record gets written to DynamoDB, any create, update, or delete actions will then be streamed out, and we can take actions on that stream of data. So now we can guarantee that when we publish the event or start the workflow, we know that the record is successfully in the database. And this same pattern can also work as a really nice way to add a anti-corruption layer or to do integration events in domain-driven design, because you've got that extra layer before you actually send the event to your event bus. Secondly, let's have a look at message channels. So in our patterns-based design, we've got a point-to-point request channel, we've got a response channel and a dead letter channel. Now, if we were to dive straight into implementation details, there are a whole raft of different services that could do that on AWS. You've got SQS, SNS, EventBridge, Managed Kafka. There's all these different services that could potentially support passing messages from system to system. So what we're doing in the first instance is we're just designing with patterns, and then we'll look at what requirements we have. Well, we need durability, we need a guaranteed single receiver, and we need error handling. Okay, so that, based on these two options here, kind of gets rid of SNS, because SNS doesn't have durability built into it, neither does EventBridge. So now we've landed on SQS. If we use SQS first in, first out queues, that also supports the single receiver and guaranteed one-time delivery. And we can also really easily hook in our error handling with a dead letter queue. And the same applies to our response channel coming back, because remember, we also want that durability there. And then we've got our work being done by the external system. So here we just need to wait for some kind of callback that uses a correlation ID and a return address. And that kind of thing can be done with AWS step functions. So as part of step functions, you can send a task token as part of a published message, and then the workflow will just wait until a response is received. So in this example here, we get a message sent to our request channel, which includes a correlation ID, our task token, and also a reply address, the reply address being the reply channel. Our receiver goes off and does its work, sends the message to the reply channel, and then we can go off and continue our workflow. So we've covered 3 really simple patterns there, but what I hope that has started to show you is that when you start to think about your systems in patterns, it can help understand the requirements of a system before getting bogged down in the specific services and implementation details. And remember, our human ability to recognize patterns and take these mental shortcuts to infer what's going to happen is one of the things that really sets us apart. Once you've implemented a transactional outbox pattern a few times, you remove the cognitive load to build and design that requirement again. You need that architectural characteristic. Well, here's an implementation. And using infrastructure as code, you could even codify some of these implementations as ready-built modules, as CDK constructs, Terraform modules. And the final thing I want you to take away, and this is a really important point outside of the technical stuff, is to bring that ubiquitous language to your architectures. Think about your colleagues, people new to the industry, or even veterans who are maybe new to the cloud provider that you're using. Having a ubiquitous language from your application code, through your integrations, through your high-level architectural things with domain-driven design, really helps to keep everyone on the same level, both technical and not technical. It removes the biases from our service choices and helps us build systems that have been tried and tested using patterns over years and years of real-world implementations. Thank you very much for listening.